Most people think the hardest part of living on the moon would be getting there, but the real challenge starts after landing. That is when gravity feels wrong. Dust gets into everything. Radiation controls your limits, and even air, water, and power become daily survival problems. The first year would not feel like living on the moon yet. It would feel like learning how not to lose against it. But before we continue, please subscribe to the channel to give your support. Let's continue. The first reason your first year on the moon would be so hard is simple. Your body would stop trusting gravity. People usually hear that the moon has lower gravity, and they jump to the wrong conclusion. They think lower gravity means easy movement, easy lifting, easy living. That is not how it works. On the moon, gravity is only about 1/6 of Earth's. You would weigh a lot less there, but your mass would stay exactly the same. That one detail changes everything. A tool bag would pull down on you less, but it would still resist motion the same way it does on Earth. A battery pack would feel lighter when you pick it up, but once it starts swinging, it still has the same inertia. A sample box would be easier to hold up, but not easier to stop if it shifts in the wrong direction. So your brain would get one message, this is light, but physics would give you another message, this thing can still throw you off balance. That is why the moon is not close to weightlessness, and it is definitely not close to easy. It is a place where your instincts become unreliable very fast. And that creates the next problem because once your instincts are wrong, even walking stops being normal. You have spent your whole life moving in 1G. Every step you take on Earth depends on that without you noticing it. Your balance, your stride length, the way you lean forward, the way you stop yourself from falling, the way your feet push off the ground. All of that was trained by Earth. On the moon, that training would no longer match the environment. You would not casually walk the way you do here. You would have to learn a different way to move. And that process would be awkward from day one. We already saw a version of that during Apollo. The astronauts did not move with a normal human gait. They bounced, they hopped. They used short loping motions because regular walking was inefficient and unstable. And those were short missions, with trained astronauts who knew they only had to operate for a limited amount of time. They were not trying to make lunar movement feel routine for months. That is the big difference. A few hours of strange movement is one thing. Living with it every day is another. During your first year, locomotion would not be a solved problem. It would be a daily operational problem. Going outside, carrying gear, climbing in and out of vehicles, moving through airlocks, working on uneven ground, turning around in a bulky suit. All of it would take more thought than it should. Then the problem gets more serious, because this is not only about awkward movement, it is also about what low gravity does to your body over time. The moon is not 0G, but it is still low enough that your bones and muscles may not get the loading they are built for. On Earth, your body is always working against gravity. That constant load helps maintain muscle strength and bone density. Remove too much of it, and your body starts adapting in the wrong direction. It starts cutting back on tissue it thinks it does not need. In space, that can mean bone loss and muscle loss, unless astronauts follow aggressive exercise routines. On the moon, partial gravity might help, but the hard truth is that we do not yet know if 1/6 G is enough to fully protect the human body during long stays. That uncertainty would make the first year especially difficult. You would not just be living on the moon, you would be living inside an active test of human biology. Every day would come with the same question. Is this gravity enough to keep you healthy? Or is your body still weakening in ways that are harder to notice at first? Exercise would not be optional. It would not be something you do for fitness. It would be part of survival. Squats, resistance training, treadmill sessions, loading routines, all of that would become basic maintenance, like charging batteries or checking filters. If you skipped it, you would be increasing the risk that your own body starts becoming less capable month by month. And there is another part of this people underestimate: falling. On Earth, a fall is usually just a mistake. On the moon, a fall can become a full systems issue. You would be moving in a pressurized suit, carrying life support hardware, with limited mobility, reduced dexterity, and a very different center of mass. Low gravity means you fall differently, but it does not mean you fall safely. You can tip in strange ways, bounce in ways your body is not used to, and struggle to recover because the suit does not move like your body wants it to. If you go down badly, you are not just bruising yourself. You might damage a suit component, contaminate a seal with dust, waste oxygen, damage tools, or end the EVA early. So something that sounds minor from Earth can immediately turn into lost work time, lost consumables, extra maintenance, and extra risk. That would force changes everywhere. Boots would need redesigns. Floor layouts inside habitats would need to reduce trip hazards. Handholds, ladders, suit joints, rover steps, workstations, storage systems. All of it would have to account for the fact that humans are less stable in reduced gravity, especially while suited. That is one of the main reasons the first year would be so hard. You would not arrive in a mature system built around human movement on the moon. You would be part of the first group trying to figure out what that system even needs to look like. And that leads to the deeper point. There would be no truly normal day for your body. On Earth, basic movement fades into the background. You get up, walk, lift, turn, sit, climb. And most of the time you barely think about any of it. On the moon, movement would stay in the foreground. It would keep asking for your attention. Every trip outside would require effort. Every heavy object would need care. Every task in a suit would cost more energy than expected. Every day would include some level of physical management because the environment would not allow your body to relax into routine. That constant demand is a big reason year one would feel harder than later years. Later crews might inherit better suits, better floor plans, better exercise systems, better tools, better habitat layouts, better movement strategies. The first crew would not have any of that at a mature level. They would get the early version, the version that still needs to be improved through real use. That means they would pay the full price of trial and error. They would be the ones discovering which motions are inefficient, which tasks are exhausting, which suit joints fight the body, which loads are harder to manage than expected, and which design ideas looked fine on Earth but fail in 1/6 G. So the first year would not be hardest because of one dramatic accident. It would be hardest because the body would never get to stop adapting. Gravity would feel wrong, movement would feel inefficient, exercise would become mandatory maintenance, and even a simple stumble could turn into a mission problem. The moon would keep reminding you of the same fact over and over. You are not built for that environment, and you do not fully know yet how to compensate for it. And once your own body stops trusting something as basic as gravity, the next problem gets worse. Because the moon also breaks something just as basic: your sense of time. The moon would break one of the most basic systems in your body, your sense of time. On Earth, time feels natural because the planet keeps feeding your body the same signals. Morning light comes in, the day gets brighter, the sun moves. Evening comes, darkness settles in, and your brain keeps using that pattern to regulate sleep, alertness, mood, hunger, and energy. You do not usually notice that system because it works in the background. On the moon, that background disappears. A lunar day, meaning one full cycle from sunrise to sunrise at the same location, lasts about 29.5 Earth days. At many places on the moon, that means roughly 2 weeks of sunlight, followed by roughly 2 weeks of darkness. So the outside world would stop giving you the timing signals human biology expects. Sunrise, noon, sunset, night. Those ideas would still exist technically, but they would stop working in any human way. From the start of your first year, the environment around you would be running on a clock that does not match the human body at all. That matters more than people think, because humans do not just use clocks on the wall. Your brain uses light as a biological instruction. It uses regular changes in brightness and darkness to decide when you should feel awake, when you should start winding down, when hormones should rise or fall, and when sleep should come more easily. On the moon, if you tried to let the outside environment set that rhythm, your body would be pushed into something completely unnatural. 2 weeks of daylight is not normal. 2 weeks of darkness is not normal. And living through that over and over would not feel like a strange detail. It would affect how you think, how you work, how you sleep, and how stable you feel. That is one reason the lunar South Pole matters so much, and it also shows how even the better option still comes with a cost. The South Pole is attractive because some high areas there can receive sunlight for much longer periods, in some cases almost continuously. That is a huge advantage for power and thermal control. If you are trying to run a base with solar energy, that kind of lighting is far better than spending 2 full weeks waiting through darkness. But it does not solve the problem cleanly. It replaces one bad condition with another. At the poles, the sun stays very low in the sky, just skimming near the horizon. Instead of rising high overhead, the way people are used to on Earth, it can sit only a few degrees above the horizon for very long periods. That creates long shadows, extreme contrast, and terrain that is hard to read correctly. A crater rim, a slope, a boulder field, even a small surface change can hide inside shadow in a way that is visually misleading. So the places that help you with power also make visibility stranger and the environment harder to read. Even the best locations on the moon are only better in comparison to something worse. And then you get to the deeper issue, because once the outside light stops being useful, your daily rhythm has to be created artificially. That means your schedule would not really come from the sun anymore. It would come from habitat lighting, software timing, alarms, medical rules, and strict operational discipline. The base would need to decide when morning begins, when work begins, when meals happen, when quiet hours start, when exercise happens, and when sleep is protected. All of that would need to be controlled on purpose because the outside world would not help you. A lunar outpost would have to manufacture a human day inside a place that does not provide one. That sounds manageable at first until you realize how easy it is for that system to get disrupted. Space crews already deal with circadian misalignment and poor sleep, even in environments that are much closer to Earth operations. If that already causes fatigue and poorer sleep quality, then a lunar base adds even more pressure. You would have shift work. You would have mission-critical operations. You would have maintenance events that do not care whether it is supposed to be your sleep period. You would have emergency EV, as that might need to happen based on power, thermal, or hardware conditions, not based on whether your body feels rested. So even if the habitat tries to create a stable day-night cycle with lights and schedules, the mission itself would keep trying to break it. That is why fatigue becomes much more dangerous on the moon than people expect. Sleep loss is never just about feeling tired. On the moon, being tired would make every other hazard worse. It would mean slower reactions during EVA. It would mean more mistakes during checklists. It would mean worse judgment when something unexpected happens. It would mean navigation errors in bad lighting. It would mean weaker communication inside the crew. It would mean less patience, more irritability, and poorer emotional control inside a small habitat where everyone depends on everyone else. One tired person does not just become less productive. That person becomes a higher risk operator in a place where small mistakes can cascade quickly. And that is what makes this section more serious than it sounds. People hear sleep problems, and they think discomfort. On the moon, sleep problems would be a safety issue. A crew member who is mentally off by even a small amount is more dangerous in a suit, more dangerous around life support systems, more dangerous during repairs, and more likely to make a bad call under pressure. The moon already gives you awkward movement, dust, radiation, thermal stress, and complex logistics. Fatigue makes all of them harder at once. That is why time becomes a real hazard. Not because clocks stop working, but because your body stops getting the normal pattern it needs to stay reliable. There is also a psychological side that would hit harder than people usually expect. On Earth, time has emotional structure. A hard day ends. Morning often feels like a reset. A rainy stretch passes. A week has a shape to it. Even people who never think about this are still using those patterns. The moon would take most of that away. In many places, darkness would last for hundreds of hours. Even at the South Pole, the sun would stay low and strange, never really giving you the clean visual reset that people are used to. That means the environment outside would not help mark time in a comforting way. Days could start feeling more artificial, more repetitive, and harder to separate from each other. During your first year, that could make the mission feel longer than it is, because the outside world would not give you the normal sense of progression people rely on without realizing it. And that is the brutal part of it. The moon would not just challenge your body physically, it would make life feel temporarily unnatural. You would be trying to build a human routine inside a place that does not support one. You would need to decide when the day begins, when work matters most, when sleep is protected, when the crew slows down, and how to stop fatigue from quietly building into bigger risks. Later, a mature lunar base might handle that better with better lighting systems, better schedules, better medical monitoring, and more refined operations. In the first year, those systems would still be getting tested in real life. The first crew would be the group finding out which routines actually work, which schedules break down, and how much discipline it takes to keep a human day alive on a world that does not have one. So the first year would feel hard not only because the moon is dangerous, but because it would keep pulling you out of sync. Outside, the light cycle would be wrong. Inside, the schedule would have to be enforced. Sleep would need protection. Fatigue would always be close. And over time, that would affect judgment, mood, teamwork, and safety. The moon would not just ask whether you can survive there. It would ask whether you can stay mentally sharp in a place where the passage of time itself stops feeling normal. And once the moon breaks both your movement and your sense of time, the next problem gets even worse because now the environment starts attacking the hardware that keeps you alive. The moon does not have weather, but it can still destroy your equipment with temperature alone. That sounds wrong at first because on Earth we connect extreme temperature with storms, wind, moisture, clouds, and seasons. The moon has almost none of that. No real atmosphere, no rain, no moving air, no weather system rolling in from somewhere else. But that does not make it gentle. It makes it harsher in a different way. In sunlight, the surface can get extremely hot. In darkness, it can become brutally cold. Near the equator, the normal swing is already severe, with daytime temperatures hot enough to overheat exposed hardware, and nighttime temperatures cold enough to shut systems down if they are not protected. In permanently shadowed polar craters, it gets even worse. Some of those places are so cold that they rank among the coldest known environments in the solar system. So your first year on the moon would not include weather reports, but it would include a constant fight against a temperature range that can damage almost everything you bring there. And the reason this gets so dangerous so fast is simple. On the moon, heating and cooling do not work the way your Earth-trained brain expects. On Earth, air does a lot of invisible work for you. It carries heat away. It spreads warmth. It helps cool machinery, skin, electronics, and structures through convection. On the moon, that option is basically gone. There is no meaningful atmosphere to carry heat away from a hot surface, and there is no warm air to soften a deep, cold shadow. That changes thermal control completely. A habitat cannot just sit there and trust the environment to balance out. A suit cannot depend on airflow outside to help remove excess heat. A rover cannot assume that stopping in one place is harmless. Everything has to manage heat through hardware, insulation, surface coatings, radiators, buried lines, thermal storage, controlled fluid loops, and active power-consuming systems. That is why temperature on the moon becomes an engineering problem, not just a background condition. If a piece of electronics overheats, it is not just uncomfortable, it can fail. If a valve gets too cold, it can stop functioning properly. If a battery spends too long in the wrong thermal range, performance drops, charging changes, and life expectancy can collapse. In year one, that would make thermal management one of the most important parts of survival. A crew might do a month of science correctly, complete every checklist, and still get into serious trouble because one radiator underperformed, one storage tank got too cold, or one internal equipment rack built up more heat than expected. The moon would not care how successful your mission looked on paper. If the thermal system slips, the whole outpost feels it. Then the problem becomes even more precise. Because on the moon, shadow is not just darker ground. Shadow can act like a thermal trap. That matters especially near the South Pole, where the sun stays low to the horizon. Instead of a high overhead sun, lighting the surface in a familiar way, you get long shadows, sharp boundaries, and strong contrast. One part of a rover can be in direct sunlight, while another part sits in deep cold. One side of a cable run can warm up while the shaded part behaves completely differently. A camera mast, a battery housing, a suit backpack, a sensor head. All of them can cross thermal boundaries quickly depending on where they are pointed and where they are parked. That means sunlight and shadow are not just visual conditions. They change how machines behave. Step into sunlight and components can heat quickly. Move into shadow and temperatures can fall just as fast in ways that affect lubricants, sensors, power draw, and mechanical performance. For a lunar base, that turns simple decisions into thermal decisions. Where do you park the rover? Where do you place the comms mast? Where do you run exposed cables? Where do you put external storage? When do you schedule EV? As so a suit does not overheat during one task and overcool during the next. During the first year, crews would spend huge amounts of time learning those patterns. Because every mistake teaches the same lesson, the moon punishes bad thermal assumptions. And then you get to one of the cruelest parts of the entire lunar story. The places most likely to hold useful water are also some of the hardest places to work. The polar regions are attractive because they may contain water ice trapped in permanently shadowed areas. That matters for drinking water, oxygen production, fuel production, and long-term survival. But those same areas are deep cold traps. They have not seen sunlight for extremely long periods. They are hard to map clearly, hard to enter safely, hard to keep equipment warm inside, and hard to operate in without adding major thermal support. So the moon creates a very direct trade-off. The resources that could make long stays possible are concentrated in places that are operationally difficult and thermally hostile. That means your first year would involve a constant decision between easier conditions and more useful terrain. Stay in better lit areas and life gets more manageable. But access to key resources may be worse. Push into darker, colder terrain, and you get closer to the materials that can support a permanent base. But your risk goes up. Your equipment gets stressed harder. Your power demands increase. Your timelines get tighter. Your margins shrink. That is one of the big reasons year one would be so hard. You would not just be surviving temperature. You would be making strategic choices based on it every day. And that leads to the larger truth. Before you build a real settlement on the moon, you first have to build a thermal machine that can keep humans alive there. A first-year lunar base would not feel like a town. It would not feel relaxed, open, or forgiving. It would feel like a tightly controlled system that exists to keep critical components inside acceptable temperature ranges. Habitat walls would be designed around heat control. Storage tanks would be placed based on thermal stability. Landing zones would be planned with heat, dust, and sunlight angles in mind. Suit ports, rover shelters, battery banks, external tool racks, power lines, even waste handling. All of it would be shaped by temperature. The outpost would only look simple from a distance. Up close, almost every design choice would trace back to one question: how do you stop this place from overheating, freezing, or cycling itself into failure? That is why the first year would feel so intense. Later on, a mature base might have buried infrastructure, better shielding, more stable thermal storage, better route planning, more reliable radiator systems, and hard-earned local knowledge about where the danger zones are. The first crew would not have that. They would be the ones learning which surfaces get too hot, which shadows are too cold, which materials degrade faster than expected, which parked positions are unsafe, and which hardware setups only looked good in testing back on Earth. They would be living inside the rough draft of lunar thermal survival. So temperature on the moon would not be a side issue. It would shape the whole base. It would decide how you store water, how you protect batteries, how long equipment lasts, where work happens, when EVAs happen, how habitats are built, and how much failure margin you really have. The outpost would not just be living on the moon. It would be constantly pushing back against a thermal environment that can quietly ruin electronics, freeze systems into silence, and force critical operations to stop. And once the moon starts attacking not just your body and your schedule, but every machine you depend on, the next threat gets even worse, because now the danger becomes invisible. Radiation would control your mission, even when nothing looks wrong. That is what makes it different from almost every other lunar hazard. Dust gets on your suit. Cold affects your hardware. Low gravity changes the way you move. You can feel those problems, or at least see their effects. Radiation is harder because most of the time it gives you no warning at all. You do not see it building up. You do not hear it. You do not step outside and immediately feel that the environment is damaging you. But on the moon, radiation would be there every day, setting limits on what you can do, how long you can stay outside, where you can sleep, how thick your walls need to be, and how quickly your base has to become more protected. The basic reason is simple. The moon gives you almost none of the shielding that protects you on Earth. Earth has a thick atmosphere and a global magnetic field. Together, those block or reduce a huge amount of harmful radiation coming from space. The moon has neither in any useful sense. It does not have a real atmosphere that can protect you, and it does not have a global magnetic shield wrapping around the whole world, So the surface is much more exposed to the deep space radiation environment. That includes galactic cosmic rays, which are fast, high-energy particles coming from beyond the solar system, and solar energetic particles, which can come in dangerous bursts from the sun. On Earth, people can go their whole lives without thinking seriously about either one. On the moon, they would become part of daily planning. That would change the way the whole mission operates. Radiation would not just sit in the background as a science topic. It would become part of scheduling. When do you send people outside? How long can they stay out? Which tasks are worth the exposure? And which ones can wait? Which compartment is the safest during a radiation spike? Which area of the base is the best place to sleep? How fast do you need to add more shielding before the outpost starts becoming safer to live in? Those are not side questions. During the first year, they would be built into almost every serious decision. And this is not just a theoretical concern anymore. We already know the lunar surface is a harsh radiation environment. Measurements taken on the moon have shown that the dose there is much higher than what people experience on Earth. It is also significantly higher than what astronauts usually deal with on the International Space Station, because the ISS still sits within some of Earth's protective magnetic environment. That changes the whole emotional picture of the moon. From far away, the moon looks clean and still. It looks like a simple destination. But once you think in terms of radiation, it stops looking simple. It starts looking like a place where your body pays a biological cost every day just for being there. And that is one of the main reasons the first year would be so difficult. You would not need to make a mistake to start taking damage. You would not need a dramatic accident. You would be adding exposure simply by living and working on the surface. That does not mean every day becomes an emergency, but it does mean every day has to be managed. Radiation would become part of the accounting of life on the moon, just like oxygen, water, power, and sleep. Then there is the part that raises the tension even more, because not all radiation threats behave the same way. Some of it is chronic. Galactic cosmic rays are part of the long-term background. They are one of the reasons long stays beyond Earth are medically difficult. But solar particle events are different. Those are the ones that can suddenly force the entire mission to change. A solar storm does not care what you are in the middle of doing. It does not care if you are halfway through deploying an antenna, fixing a rover, hauling samples, or trying to recover some damaged equipment. If a radiation event starts building, your priorities change immediately. Work stops mattering as much. Exposure starts mattering more. That means your first year on the moon would include a whole layer of operations built around forecast watching, shelter drills, and rapid retreat plans. A serious surface mission could not just think in terms of task lists. It would have to think in terms of escape time. If conditions change, how fast can the crew get back inside? If they are far from the habitat, what is the nearest protected location? If there is no nearby shelter, should that EVA have happened at all? Those questions make lunar life less flexible than people assume. You're not just going outside to do work. You're going outside with a constantly moving limit over your head. And that leads to one of the most important changes in how you think about the moon, because the ground itself starts becoming part of your survival system. On Earth, dirt is just dirt. On the moon, regolith would quickly become one of the most useful materials you have. The same broken rock and fine dust that make movement harder and contaminate equipment can also help block radiation if you pile enough of it in the right places. That is why local shielding matters so much. Launching huge amounts of protective mass from Earth is expensive and limited. Using lunar material already sitting on the surface is far more realistic for building up serious protection. So during the first year, one of the biggest races would be to stop the habitat from acting like a temporary camp and start turning it into something more protected. That could mean burying modules, pushing regolith up into berms, covering certain walls, building storm shelters, and deciding which parts of the base need the most shielding first. In other words, the outpost would not become truly livable just because it landed successfully. It would become more livable only as more local material gets moved into place and the base becomes thicker and safer. That is why the first year would be harder than the fifth. Later crews would inherit more protection. They would have better shelter layouts, more tested procedures, more practiced retreat timelines, and more local shielding already in place. They might sleep inside better protected spaces. They might work from a base that has already been covered, reinforced and organised around radiation risk in a smarter way. The first crew would not get that advantage. They would be living through the most exposed version of the base. And that matters because year one combines all the worst conditions. Thin infrastructure, limited shielding, less local material, already positioned where you need it, less operational experience, less certainty about exactly how the terrain affects line of sight, shelter access and surface planning. So radiation would not just be a danger from space, it would also be a measure of how unfinished your habitat still is. That is the real reason radiation becomes the invisible boss of the mission. It does not need to be dramatic to shape everything. It sits over crew schedules, habitat design, EVA planning, sleep location, emergency procedure, and construction priorities. It decides how fast the base needs to mature. It decides which walls matter most. It decides how much risk you are accepting every time someone leaves a shielded volume. And because it is mostly invisible, it is easy for people on Earth to underestimate how much control it would have over daily life. So the first year on the moon would not just be hard because space is dangerous in a general sense. It would be hard because radiation would keep reminding you that arriving is not the same as being protected. A landed habitat is not yet a safe habitat. A successful EVA is not yet a low-risk EVA. A working outpost is not yet a mature one. Until the walls are thicker, the shelters are smarter, and the procedures are fully shaped by real experience, every month on the lunar surface would carry that same message. You are living outside Earth's protection, and your base is still trying to catch up. And once the danger becomes something you cannot see but have to plan around every day, the next problem gets even more frustrating, because now the thing attacking your mission is everywhere, and it follows you home. Dust would become the problem that never really leaves. A lot of people think of lunar dust as a small nuisance, something like dirt on boots, or powder on a surface that you can wipe away and forget. That is not what it would be. On the moon, dust would behave more like a slow attack on everything that matters. It covers almost the whole surface, and it was made over immense spans of time by constant impacts and space weathering. But the real issue is not just that there is a lot of it. The issue is what it is like. Lunar dust is extremely fine. It sticks to surfaces, it is abrasive, and many of the particles are sharp. So from the start of your first year, dust would stop being a cleanliness problem and turn into a systems problem. It would get on suits, into joints, onto seals, across visors, into airlocks, onto tools over sensors, around connectors, and eventually into the living space unless your procedures are very good. On Earth, dust is annoying because it makes things dirty. On the moon, dust would matter because it degrades hardware, threatens air quality, interferes with cooling, scratches surfaces, and keeps spreading from one place to another. That is why it would be one of the most relentless enemies of a lunar base. It would not need one dramatic moment to hurt you. It would keep causing small losses over and over again, until your maintenance time, your cleaning burden, and your risk level all start rising together. And the warning signs are not hypothetical. Apollo already showed that lunar dust can follow astronauts back inside and affect their bodies. The Apollo missions were short, but they still gave a clear preview of the problem. Dust came in on suits, got into the cabin, and irritated the astronauts. They reported symptoms like sneezing, congestion, and throat irritation after exposure. That matters because those missions only involve brief contact compared with what a real lunar outpost would face. A first-year crew would not be dealing with dust for a few days. They would be dealing with it repeatedly, for weeks and months, with more EVAs, more equipment transfers, more suit cycles, and more chances for contamination to build up. That is what makes this so serious. We already know short exposure can cause irritation. What we do not fully know is what repeated exposure does over long stays in a working base. What happens to lungs after months of trace contamination events? What happens to eyes, skin, filters, seals, and interior surfaces when the crew keeps bringing back small amounts again and again? That is the hard part of year one. The base would not just be surviving dust. It would be helping to find the real limits of long-term human exposure to it. And even if dust never seriously injures a crew member directly, it would still attack the mission through the machines. That may be the more dangerous side of it, effective day operations. Dust does not just sit there. It gets into moving parts and starts increasing wear. It coats suits and makes them harder to clean. It roughens visors and reduces clarity. It works into seals and can raise leak risk over time. It settles on thermal control surfaces and changes how well they work. It gets into interfaces that need to stay precise. A shoulder joint that worked smoothly before may start resisting motion more. A hatch seal that looked fine may start needing extra inspection. A radiator surface that needs to stay efficient may slowly lose performance because fine abrasive material keeps building up on it. That is one reason the first year would be so punishing. Every moving part in the outpost would be getting its first real lesson in lunar contamination. Designs that look strong in testing on Earth may start failing faster when real dust gets into them. Maintenance schedules might grow, cleaning procedures might become longer, consumables might get used faster. Crew time that was supposed to go to science or construction could start getting pulled into inspection, brushing, wiping, replacing covers, checking seals, and dealing with gear that no longer behaves like it did when it first landed. That is the hidden way dust raises the cost of life on the moon. It turns simple systems into higher maintenance systems. It forces every task to carry extra contamination control with it. And because the damage builds gradually, it is the kind of threat that can be underestimated until a lot of small problems suddenly add up. Then there is the uncertainty that makes it even harder to manage, because dust on the moon may not always stay where you expect it to stay. Some research suggests lunar dust can be influenced by charging effects from sunlight and plasma. And that means at least some dust behavior may depend on lighting conditions and the local environment in ways that are still not fully settled. That does not mean the whole surface turns into a floating cloud, but it does mean there are still open questions about how dust moves naturally in certain conditions, especially near the boundary between light and dark. For a first-year crew, that matters, because uncertainty is its own kind of hazard. You are not just dealing with the dust you know you kicked up. You are also dealing with transport behavior that may not yet be fully characterized in real lunar operations. Even without the more uncertain effects, the operational reality is already bad enough. Every landing throws material around. Every rover drive disturbs the surface. Every EVA creates another contamination pathway. Every piece of dirty hardware that comes back near the habitat becomes a decision point. Does it stay outside? Does it go into a transition zone? Does it need brushing, isolation, sealing, replacement, or extra filtration support? On the moon, dust would spread through activity itself. The more active the base becomes, the more it has to control the contamination created by that activity. That is why year one would involve building not just a habitat, but an entire anti-dust culture. You would need strict rules for airlocks, strict rules for cleaning, strict rules for what hardware is allowed where, and strict rules for how dirty surfaces are handled before they come near crew living areas. Suit systems would need to reduce how much dust comes inside. Filters would need layers and replacement plans. Materials would need to tolerate abrasion better than normal. Covers might need to be sacrificial, meaning they are expected to take damage and get replaced. Tools would need to be designed for cleaning as well as for work. Storage areas would need clean and dirty zones. The base would need procedures that sound almost obsessive. Because on the moon, if you are casual about dust, the dust starts spreading into everything. That is a very different kind of frontier challenge than people usually picture. Early settlements on Earth had weather, disease, hunger, isolation, and supply problems. A lunar base would have those kinds of pressures in its own way, but it would also have something else, an abrasive powder that can ride back with you from almost every surface operation and slowly damage both people and hardware. That means daily life would include a level of contamination discipline far beyond normal human experience. The first year would not just be about surviving on the moon, it would be about inventing basic hygiene for a place where the ground itself is one of your main operational enemies. And that is why dust may end up being more exhausting than the dramatic hazards. Radiation is invisible, but at least you can build shielding and retreat into shelter. Temperature is harsh, but you can model it and design around it. Dust gets personal. It sticks to the suit that keeps you alive. It follows you back to the hatch. It settles into the mechanisms you depend on. It raises wear, raises maintenance, raises uncertainty, and keeps demanding attention long after the EVA is over. So during the first year, one of the biggest jobs would not be exploration, in the heroic sense. It would be contamination control. It would be trying to stop a grey, abrasive, clingy material from turning every successful outing into a new wave of cleanup, repair, and risk. The moon would keep teaching the same lesson, again and again. The surface is not just where you work, it is something that comes back with you. And once even the dust starts acting like an enemy, the next problem becomes even more personal. Because now the thing standing between you and the moon is a machine you have to wear on your body, and it fights you the whole time. Your spacesuit would not feel like clothing. It would feel like a machine you have to wear correctly every single minute. That is the first thing people miss about life on the moon. Going outside would not be a casual action. It would not be like stepping out of a house, or even like going out into a dangerous desert with the right gear. On the moon, the outside is vacuum. There is no breathable air, no useful pressure, no weather you can adapt to with a jacket or a shelter nearby. So the moment you leave the habitat, you stop relying on the life support systems of the base and start relying on the life support systems built into your suit. That means your suit has to do everything at once. It has to keep pressure around your body, it has to feed you oxygen, it has to remove carbon dioxide, it has to manage heat, it has to power communications, it has to let you move, it has to keep dust out as much as possible. So every EVA would really be a transfer from one controlled survival system to another. That changes the meaning of something as simple as going to work. On Earth, leaving the building is nothing. On the moon, leaving the habitat would trigger a whole chain of procedure. Checklists, seal inspections, leak checks, battery status, oxygen margins, thermal planning, comm checks, route planning, tool tracking, dust management, return timing, contingency timing. All of that would happen before you even start the real task. And that is why the first year would feel so intense. The work outside is not the only thing costing you time. Just becoming ready to go outside would already be a major operation. And once you are out there, the suit starts deciding how much of the moon you can actually use. A lunar base might look impressive on a map, but the real size of your world would be limited by what a suited human can do safely. How far can you walk before you need to turn back? How much can you carry before your movement becomes inefficient? How long can you work before your cooling system, battery, and consumables start becoming the dominant concern? How much time can you afford to lose if one connector takes longer than expected? Or if one tool is harder to handle than it looked in training? Those are the questions that turn the suit into more than protective gear. The suit becomes the boundary of your civilization. That is especially important in year one, because early lunar operations cannot afford much inefficiency. Apollo missions could tolerate awkward movement and time loss because the sorties were short, and the whole program was built around brief surface visits. A first-year outpost is different. It has to convert short-term exploration habits into long-term working habits. That means every stiff joint in the suit matters. Every awkward glove motion matters. Every minute lost because a handrail is hard to grip, or a panel is hard to unlatch, or a cable is hard to connect matters. Those minutes turn into less work done, more fatigue, more exposure, and tighter safety margins. So the suit would directly control productivity. If the suit is hard to move in, then the moon itself becomes smaller, slower, and more expensive to operate in. And there is another problem that makes suits even more dangerous than they sound. Because the suit does not just protect the habitat from the moon, it can also carry the moon back inside. That is where every EVA return becomes tense. Dust gets on the outer surface. It sticks to fabric, joints, boots, gloves, and hardware. If the return procedure is weak, the suit becomes a contamination carrier. Then the problem is no longer just outside. It comes right up to the airlock. What gets brushed off before entry? What stays outside? What tools come in? Which surfaces are treated as too dirty to cross into the living volume? What gets filtered? What still comes in on seals, on connectors, on surfaces people missed, on parts of the suit that were harder to clean than expected? That is the kind of problem a mature base might eventually handle with polished routines and better equipment. In the first year, those procedures would still be improving through trial and error. That is what makes it difficult. The crew would not just be following final perfected rules. They would be discovering which rules are not good enough. One bad airlock sequence could mean more dust in the cabin, more irritation, more cleaning, more filter load, more wear, and more risk building up over time. So the suit would not only be your protection outside, it would also be one of the main contamination threats to the habitat if it is handled badly. Then there is the problem that starts before the EVA even begins, because the landing zone itself can become a source of suit trouble. Every new landing can throw dust and particles across the surface. Rocket exhaust interacts with the ground violently. It can erode the regolith, kick up debris, and spread abrasive material over nearby systems. That means every arrival and departure has the potential to make your operating area dirtier and harder on equipment. In year one, this would be especially bad because the base would still be young. Permanent landing pads might not be fully developed. Protective berms might not be thick enough. Layouts might still be in an early stage. So when new cargo comes in, or a new crew arrives, the very act of supporting the base can also make the local environment worse for the suits and hardware already there. That creates a brutal loop. You need logistics to expand the outpost, but each landing can spread more dust, increase more abrasion, and make future suit operations harder. So the moon would punish you for growing before your infrastructure is ready. And because the suit is the one system that has to physically carry people through that environment, it absorbs a lot of that punishment directly. That is why life on the moon in year one could never feel casual. A real settlement feels easy at the surface level. Doors open, people move, work happens, routine takes over. A first-year lunar outpost would not feel like that at all. Every time someone leaves the habitat, the whole process would feel procedural and expensive. It would cost power, consumables, prep time, cleanup time, and attention. It would always carry some level of tension, because the suit is doing too many critical jobs at once. If mobility is worse than expected, the mission slows down. If cooling struggles, the timeline changes. If dust comes back in, the habitat pays for it. If a seal is damaged, the whole system becomes more fragile. That is why the suit would keep feeling like it is fighting you. Not because it is poorly designed, but because it is being asked to solve too many lunar problems at the same time. And that is the deeper reason this section matters so much. People think the hard part of the moon is the distance, or the landing, or the danger outside. But in year one, the real difficulty is that human presence is still mechanically fragile. You are alive outside only because a wearable spacecraft is functioning correctly, and because everyone around you is following procedure with almost no room for laziness. That is not yet normal life. That is survival made routine, but still not made easy. Later on, better suits, better suit ports, cleaner landing zones, tougher interfaces, and better dust control could make lunar operations feel less tense. But the first year would come before that maturity. The first crew would be the ones working through the awkward stage, where every EVA still feels like a carefully managed event. Every return still risks contamination. And every hour outside still depends on hardware that has to perform almost perfectly. So your first year on the moon would not feel like people simply stepping out into a new world. It would feel like people repeatedly placing their lives inside a machine, sending that machine into vacuum and dust, and hoping procedure, engineering, and discipline are strong enough to bring everyone back clean and intact. And once even stepping outside becomes that complicated, the next problem gets bigger, because now the most basic things in life, air, water, and food, stop being supplies and start becoming industries. The moon would turn the basics of life into full-time industrial work. On Earth, you do not usually think about where your next breath comes from, where your water really starts, or how hard the planet is working to keep food growing somewhere. Those systems feel automatic, because Earth gives you a huge safety margin. The moon does not. The moon does not give you breathable air, open water, useful soil, or any living ecosystem already doing the work for you. It gives you rock, dust, trace volatiles, and the possibility that some of what you need is trapped in places that are difficult to reach and difficult to process. That is why your first year would be so hard. Breathing, drinking, and eating would stop feeling like background parts of life. They would become production problems. And that changes the whole mood of a lunar base, because once life support depends on extraction, every day starts looking more like operations than survival in the simple sense. You are not just living inside a habitat. You are running a small industrial system that has to keep turning raw material into something a human body can use. Water has to be found, collected, purified, stored, and recycled. Oxygen has to be brought in, reclaimed, or eventually extracted. Food has to be shipped, preserved, rationed, supplemented, and maybe partially grown under very controlled conditions. Nothing about that is casual. Nothing about that has much slack in year one. That is why the poles matter so much, and also why they are so frustrating. Water ice is one of the biggest reasons the lunar poles are strategically important. Water is not just for drinking. It matters for hygiene, for oxygen production, for cooling systems, and potentially for fuel if you can split it into hydrogen and oxygen. So when people talk about long-term survival on the moon, water is always near the centre of the conversation. The problem is that useful water is concentrated near or inside permanently shadowed regions, and those are some of the hardest places to work. They are dark, cold, difficult to map, difficult to enter, difficult to keep equipment operating in, and difficult to connect into a reliable extraction system. So from the beginning, year one would be defined by a harsh trade-off. The resource you need most is located in one of the least friendly operating environments on the moon. Every kilogram of extracted water would represent real cost. You would spend power to get it. You would expose machines to dust and cold to get it. You would take thermal risk to get it. You would commit crew time or robotics time, or both to get it. That means water on the moon would not feel abundant even if the resource is genuinely there. It would feel expensive, because every step between ice in the ground and usable water in a tank is difficult. And even if you solve water partly, the next problem stays just as strange, because on the moon the air you need is not above you. It is locked inside the ground. That is one of the most important things to understand about long-term lunar life. Lunar soil contains oxides, and those oxides contain oxygen. That sounds promising. And it is, but it also means oxygen production becomes a processing problem. You do not step outside and gather air. You do not drill a simple well and suddenly have everything you need. You have to take regolith, heat it aggressively, run it through industrial processes and separate out the oxygen. In other words, the moon can help you breathe, but only if you build the machinery to turn dirt into life support. That is why year one would feel so unfinished. Even if the first crew starts testing resource extraction, they would still be living mostly on imported reserves and backup systems. Local oxygen production might begin in small amounts, but it would not yet be mature enough to carry the whole outpost with confidence. So every breath would still come with an uncomfortable fact in the background. The moon contains oxygen, but it does not hand it to you. You have to earn it through heat, chemistry, equipment, and power. And in year one, all of those systems are still early, limited, and vulnerable to failure. Then there is food, which sounds simpler until you look at it closely. A lot of people jump straight to the idea of greenhouses and imagine that once humans arrive on the moon, growing food is just a matter of building a nice controlled room and planting seeds. The reality is much more demanding. Growing food off Earth is possible, but it is not easy, and the moon makes it harder because lunar regolith is not ready-made farmland. It is abrasive, nutrient-poor, and biologically dead. There is no natural soil ecosystem helping roots. There is no normal hydrology. There is no weather cycle helping distribute moisture or nutrients. So even if plants can be grown there with the right support, that does not mean the moon suddenly becomes agriculturally friendly. In the first year, any food growing effort would be more like a controlled experiment than a reliable harvest system. You would need carefully managed lighting, water recycling, nutrient delivery, contamination control, gas balance, and probably engineered growing media, rather than raw regolith alone. You would have to test what grows well, what fails fast, what stresses under lunar-derived material, what disease or mold risks appear inside closed systems, and how much crew time the whole setup consumes. That is the part people underestimate. Food production is not just a scientific achievement, it is also a maintenance burden. If the greenhouse works, it still has to keep working every day, so a first-year lunar base would not be feeding itself in any deep sense. It might begin learning, it might begin supplementing, it might prove small systems, but most of the calories would still come from Earth, packed, preserved, rationed and protected. That means food would remain part of the supply chain, not yet part of a true, local economy of survival. And that leads to the main reason this entire section matters so much. In year one, the base would still be metabolically external. That sounds technical, but the meaning is simple. The outpost would still depend on Earth for the deeper processes of life. Spare oxygen tanks, packaged food, emergency water, filters, chemicals, replacement parts, hygiene supplies, nutrient mixes, all of that would still be coming from outside. Local resource use might start, but it would not yet be strong enough to carry the base through real trouble by itself. So the first year would be the hardest because the moon has not yet become a place that supports you directly. It is still a place where you are trying to build the machines that might eventually support you. That is a very different situation from a mature settlement. Later crews might arrive to larger reserves, better extraction systems, better recycling loops, more food production, more storage, more spare capacity, and more confidence that local industry can cover part of daily life. The first crew would not have that. They would be living in the most fragile stage, where every essential resource still feels a little too imported, and every local production system still feels like something being proven, not something fully trusted. So your first year on the moon would be hard, not just because supplies are limited, but because the basic acts of life would no longer feel simple. Breathing would connect back to tanks, recycling loops, and maybe early oxygen extraction. Drinking water would connect back to storage, reclamation, and difficult polar resources. Eating would connect back to cargo delivery, preservation, and cautious early attempts at local growth. The habitat would not just be shelter. It would be a small metabolism under construction. And once air, water, and food stop feeling automatic, the next problem becomes even more unforgiving. Because now survival depends on the one thing the moon never gives you, for free, steady power. Power would stop being infrastructure and start being survival. On Earth, when the power goes out, most people think about inconvenience first. Lights go dark, screens shut off, the internet drops. Maybe the building gets uncomfortable. On the moon, a power failure means something much worse. It can hit air circulation, water processing, communications, heating, cooling, charging, pumps, computers, sensors, life support backups, and the systems keeping the habitat stable. That is why electricity on the moon is not just electricity. It is part of breathing, part of staying warm, part of staying cool, part of staying connected, and part of staying alive. So your first year would be hard because every hour of survival would depend on a steady flow of power in a place that makes steady power difficult. And the moon makes it difficult in a very basic way, because the sunlight cycle is terrible for simple solar living. A lunar day lasts about 29.5 Earth days. At many places on the moon, that means around 2 weeks of sunlight and then around 2 weeks of darkness. On Earth, even a short winter day still gives you regular daylight again the next morning. On the moon, a bad power plan can leave you facing hundreds of hours without sunlight. That is why the first year would not just be about generating electricity, it would be about maintaining continuity through long periods when solar input can collapse. If your systems are mostly solar, then the real challenge is not making power when the sun is available. The real challenge is staying alive when it is not. That is why the polar regions matter so much. The lunar South Pole gets so much attention because some locations there can receive sunlight for much longer stretches than places closer to the equator. That is a huge advantage. It does not mean permanent, perfect lighting, but it does mean better odds of keeping solar systems active for longer periods. In a place where power is tied directly to life support, better odds matter a lot. A site with more available light is not just a nicer construction site. It may be the difference between a base that can keep functioning and a base that keeps sliding toward crisis every time the lighting changes. But even there, the moon does not make it easy. The sunlight comes in strange patterns because of terrain, crater rims, ridges, and the very low angle of the sun. So power site selection becomes much more important than it sounds. You are not just picking a scenic location, You are choosing how much margin the entire outpost will have. A badly placed base could spend too much time in shadow, lose charging opportunities, strain storage systems, and make every later decision harder. A better placed base gets more time, more flexibility, and more survivability. That is why power geography on the moon is not just geography. It is mission architecture. And even when you choose the better area, the sun still creates new problems, because low-angle light is hard to work with. At the South Pole, the sun stays close to the horizon. That creates long shadows that move across rugged terrain in ways that are difficult to manage. A solar panel does not just need sunlight on paper. It needs real exposure in a specific place at the right angle, without terrain blocking it too often. The same is true for towers, masts, antennas, and rover charging points. You might have one ridge getting relatively good light, while a nearby depression loses it much earlier. You might have hardware that performs well for part of a cycle, and then drops into shadow more often than expected. So your first year would involve a lot of work just understanding shadow drift and light access. Crews would spend time mapping where the best lit ground actually is, which structures deserve it most, and how often assets need to be moved or elevated. That would create brutal engineering compromises. Do you put the habitat in the best thermal location or the best power location? Do you give the highest ground to comms hardware, solar arrays, or crew access routes? Do you move a rover charging point closer to operations or keep it where sunlight is more reliable? Those are not small layout questions. They shape how much work the base can do. On the moon, power is not just about panels and wires. It is about who gets access to the best line of sight to the sun and who does not. Then you reach the part that is even more important than generation, storage. Because even in the best case areas, power continuity still depends on storing energy when conditions are good and using it carefully when conditions are worse. That means batteries matter, fuel cells matter, backup systems matter. And if critical hardware exists, then emergency reserves matter even more. A lunar base cannot assume that generation alone will save it. It needs enough storage and enough redundancy to keep life support, thermal control and communications running through interruptions, shadow periods, equipment faults and unexpected demand. That is why the first year would involve relentless energy budgeting. Every EVE takes power somewhere in the system. Every heater cycle takes power. Every water processing loop takes power. Every communication session takes power. Every oxygen production test takes power. Every dust cleaning system. Every pump. Every lab experiment. Every excavation attempt. Every charging event. All of it draws from the same finite electrical budget. And in year one, that budget would still feel tight. The outpost would not yet be rich in power. It would be rationing ambition based on what the system can support. That changes the whole feel of life on the moon. On Earth, people use electricity casually because the grid is deep and redundant. On the moon, every major activity would be connected to a power decision. Can you afford this EVA and this heating load on the same day? Can you run extraction hardware now, or do you need to protect battery margin first? Can you grow the food system bigger yet, or does thermal control need those kilowatt hours more? Can you expand rover range, or do you need that charging capacity for habitat resilience? Those are the questions that make year one hard. You are not just solving engineering problems, you are constantly deciding which part of civilization gets power first. And that is the real dividing line between an outpost and a settlement. A mature moon base would still care about power, but it would care from a position of strength. It would have more generation, more storage, more redundancy, better route planning, better placement of assets, better forecasting, and more experience with local lighting conditions. It could absorb mistakes more easily. It could support more science, more construction, more comfort, and more safety margin. A first-year base does not get that luxury. In year one, power is still scarce, still exposed, still tied tightly to location, and still one failure away from becoming a much bigger problem. That means almost every big goal gets bottlenecked by energy. Mining ice needs power. Processing regolith needs power. Expanding shelter needs power. Running comms needs power. Charging suits and rovers needs power. Growing food needs power. Even making the base more self-sufficient depends on first having enough electricity to support the machines that make self-sufficiency possible. So before you industrialize water, oxygen, mobility, shielding, or food, you first have to industrialize power. That is why the first year would feel so unforgiving. The moon would not just ask whether you can generate electricity. It would ask whether you can keep it flowing, store it safely, distribute it intelligently, and defend enough margin that one bad shadow, one damaged cable, one weak battery bank, or one over-ambitious work plan does not start threatening systems that humans need to survive. So the first year on the moon would not feel like a place where power supports life in the background. It would feel like a place where life is balanced directly on top of a fragile electrical system that is still growing into the job. And until that system becomes abundant and redundant, every plan stays limited by the same hard facts. On the moon, civilization runs only as far as the power reaches. And once even electricity becomes a daily survival issue, the next problem gets more serious. Because now you still need something even more basic than power, a shelter that can actually deserve the name. Landing on the moon would be hard, but building a place that can keep you alive, there would be much harder. A landing proves you can reach the surface. It does not prove you can stay. That is the difference people miss. Touching down is a transport problem. Shelter is a long-term survival problem. And the moon makes that problem difficult before construction even starts. The ground is not prepared for you. It is covered in regolith, broken by impacts, uneven, dusty, cratered, and mechanically awkward. There is very little erosion compared with Earth, so old damage stays there. That means you are not arriving at a clean building site. You are arriving at rough terrain that has had billions of years to become inconvenient. That matters immediately, because the first habitat module does not land on a smooth concrete pad. It lands in a place where dust, slopes, buried rocks, loose surface layers, and crater edges all matter. Every metre of ground has to be evaluated in terms of stability, dust movement, access, lighting, and how close it is to the other systems that will follow. A base on paper can look neat and organised. A base on the real lunar surface has to deal with the fact that the terrain chooses how neat and organised you are allowed to be. That is one reason the first year would be so hard. You would not just be building structures, you would be fighting the site itself. And then the situation gets worse because even the act of arriving can damage the place you are trying to turn into a base. Rocket exhaust on the moon is a serious problem. When a lander comes down, the exhaust can hit the surface, erode the regolith, and blast dust and particles outward at high speed. That means every landing can damage nearby hardware, coat surfaces, and make the local area harder to operate in. A cargo mission does not just bring supplies. It can also spread abrasive material across the zone you are trying to keep functional. A rescue vehicle, a crew rotation, a second cargo drop, all of those help the base in one sense and threaten it in another. That creates a difficult loop in year one. You need more equipment to make the outpost safer, but bringing in more equipment can make the local environment rougher unless you already have landing pads, standoff distances, protective layouts, or some kind of barrier system in place. And those are exactly the things you are still trying to build. So early lunar construction would be stuck in a bootstrap phase. You need infrastructure to support safer landings, but you also need more landings to bring the infrastructure. That means the base zone stays vulnerable during the exact period when it is also growing the fastest. And once the modules are down, another reality sets in, because a habitat on the moon cannot just be a sealed cylinder with air inside. On Earth, a building mostly protects you from weather and keeps the indoor environment stable. On the moon, a habitat has to do far more than that. It has to hold pressure. It has to help control temperature. It has to reduce radiation exposure. It has to keep dust out. It has to survive micrometeoroid risk. It has to support internal air quality. It may have to tolerate vibration or movement from lunar seismic activity. It has to do all of that while being limited in mass because every kilogram brought from Earth is expensive. That is why the walls of a lunar shelter would never be enough by themselves in the early stage. A delivered module may be habitable, but that does not mean it is adequately protected for long-term living. The first crew would likely be racing to improve that protection with local material, especially regolith. Piling lunar soil around modules, building berms, burying parts of the habitat, and adding shielding mass would all matter because one layer of material can help against multiple threats at once. It can reduce radiation, it can help with temperature stability, it can add protection from small impacts, it can make the habitat feel less like exposed hardware and more like real shelter. That means the habitat would not truly become what people imagine at landing. Landing would just be the start of the shelter building process. The module arrives first, but the real shelter only starts to exist once that module is reinforced, protected, and integrated into a larger survival system. In year one, the crew would be living in that gap. They would be sleeping inside hardware that is usable, but still not fully matured into architecture. And if that sounds stressful already, there is another problem that changes how you think about the ground itself, because even the moon does not stay as still as people assume. People often picture the moon as geologically dead, just sitting there quietly while humans build on top of it. That is too simple. Moonquakes are real. Some shallow ones can be strong, and they can last far longer than most people expect. That matters because long-duration shaking does not have to be catastrophic to become dangerous. It can stress structures, affect alignment, disturb equipment, and challenge anything that has not been anchored or reinforced properly. A mast, a tank, a landing vehicle, an exposed module, even a solar tower or rover shelter, all of those become more serious engineering problems when the ground itself is not perfectly still. So in the first year, shelter design would not just be about keeping air in and danger out. It would also be about structural margin. How well is the habitat anchored? What happens if the ground shifts slightly or shakes for longer than expected? How stable are connected modules, external pipes, power systems, and towers? What does repeated small stress do over time? Those are not background questions. They affect how confidently you can build outward. If your base is still young and lightly protected, even modest seismic risk feels bigger, because there is less redundancy and less proven performance in the system. That is the deeper reason shelter would be harder than landing. Landing is dramatic, but short. Shelter is permanent, layered, and full of interacting weaknesses. A lunar base has to defend against many problems at once. And if even one layer is immature, the whole system feels less secure. A module that is pressurized but undershielded is not enough. A structure that is insulated but not well protected from dust is not enough. A habitat that survives normal operations but cannot handle local shaking or repeated landings nearby is not enough. Real shelter on the moon is not one object. It is a growing set of protections that all have to start working together. And that is exactly why the first year would be the hardest. Later crews might inherit buried sections, thicker shielding, safer landing zones, stronger foundations, cleaner layouts, tested repair methods, and procedures that have already been improved by real experience. They might enter a base that already feels like a place. The first crew would not get that version. They would get the early version, where much of the shelter still exists as intention rather than finished reality. So every night in year one would carry that truth in the background. You are not resting inside a mature base. You are resting inside delivered hardware that is still being turned into a real habitat. The walls are still gaining protection. The site is still being stabilized. The landing zone is still a hazard. The local repair culture is still young. The shielding is still not thick enough. The base is still learning what kind of structure it needs to become. That is what makes this stage so demanding. You are not arriving at civilization. You are living inside its construction phase. The place keeping you alive is still becoming the place keeping you alive. And on the moon, that difference matters every single day. And once even your shelter is still unfinished, the next problem becomes unavoidable. Because now every trip outside stops looking like exploration and starts looking like logistics. Every EVA would stop feeling like exploration very quickly and start feeling like work management under pressure. That is one of the biggest gaps between how people picture a moon base and how it would actually feel in the first year. From Earth, moonwalking looks dramatic. It looks historic, open, almost cinematic. But once a base exists, the meaning of going outside changes. You are no longer going out there mainly to see something new. You are going out there to keep the whole system running. That means route planning, tool prep, battery checks, oxygen margins, dust control, thermal timing, comms checks, return windows, and contingency plans. Before the EVA even begins, it is already a logistics problem, and once it starts, the clock is always running. Apollo already gave a preview of that. Even at the most capable end of the program, surface time was limited and tightly managed. Those missions were not casual. They were heavily planned operations with very clear limits. Now stretch that into year one of a permanent outpost, and the difficulty gets much bigger. You are no longer doing short visits built around a few historic tasks. You are trying to turn surface activity into a normal part of life. That is much harder than it sounds, because the moon does not let outside work become casual. Every EVA keeps all the old constraints, and then adds the new burden of maintaining a base that cannot afford many mistakes. And the first thing that makes it hard is simple. Distance on the moon is not the same as freedom on the moon. A place can look close and still be operationally difficult to reach. That is because range is not just about meters on a map. It is about consumables, terrain, lighting, communications, and return margin. A rover might technically reach a site, but can it do that safely if something goes wrong? A crew might be able to walk a route, but can they still get back if one tool jams? If one suit takes longer than expected? If the terrain proves rougher than planned? Or if the thermal load goes up? That is what changes the feel of lunar travel. You never judge a route only by distance. You judge it by the whole chain of risks attached to that distance. That gets even worse near the South Pole, where lighting can make short traverses feel much more complicated than they should. The sun stays low, shadows stretch far, contrast gets deceptive, and slopes can be harder to read correctly. A surface that looks manageable from one angle may hide a bad patch just ahead. A path that seems clear may cut through shadow in a way that changes thermal conditions or visibility. So even a relatively short trip can become a navigation problem. Where is the safe route, not just the direct route? Where is the shadow edge moving? How dusty is the ground? How stable is the slope? Can you keep line-of-sight communications? What happens if the rover stops now instead of later? Those are the kinds of questions that turn movement into logistics. And then there is the part people almost always underestimate. Tools. Tools on the moon do not stop being tools, but they stop being simple. In 1/6 G, equipment weighs less, but it still has the same mass and the same awkward inertia. Add gloves, suit stiffness, dust, limited dexterity, reduced feel in your hands, and the constant pressure of consumables, and suddenly even routine jobs take much longer than expected. Tightening a connection, carrying a part, routing a cable, placing anchors, swapping a panel, collecting a sample, moving a storage box. All of it starts taking more time and more concentration. That is what makes first-year EV so demanding. It is usually not one impossible task. It is a long chain of medium difficulty tasks that slowly wear you down. One awkward motion is manageable. 10 awkward motions in a row start draining time, energy, and attention. A job that looks simple in a procedure manual can become frustrating outside in a suit, when dust is sticking to surfaces, visibility is imperfect, gloves are fighting fine motor control, and every delay is eating into your margins. The moon punishes cumulative inefficiency. You do not fail because one task is absurd. You fail because enough ordinary tasks become slower and harder than planned. And that is why a lot of Year 1 EVA work would not even feel exciting in the way people expect. Most of it would be support work. Not discovery, support. A lot of surface time would go into making future surface time less painful. That means laying cables, validating routes, checking dust buildup, cleaning interfaces, inspecting seals, improving shielding, setting markers, checking comms paths, verifying landing zone conditions, recovering stuck equipment, repositioning hardware, and fixing whatever the moon has already started degrading. That is the real operational shift. At first, people talk about exploration like it is the main event. In Year 1, then exploration often becomes secondary to making the base more stable, more efficient, and less fragile. That is not glamorous, but it is exactly how a frontier starts becoming real. Before a place feels open, Someone has to keep improving the basics. The first crews would spend huge amounts of effort making tomorrow slightly easier. Slightly cleaner paths, slightly better layouts, slightly safer routes, slightly more reliable hardware, slightly less dust where it matters, slightly faster turnarounds. That is what surface work would look like most of the time. You are not just collecting knowledge. You are lowering the cost of being there at all. And that leads to the larger truth. The moon would teach you that exploration is mostly infrastructure. From far away, a moon base looks like adventure. Up close, it looks like checklists, inventory, maintenance, route selection, power trade-offs, wear management, and careful decisions about whether going outside is worth the cost. Every EVA would have to justify itself. Does this job matter enough to spend the battery, oxygen, crew time, and hardware wear? Is it worth the extra dust contamination? Is it worth the risk of delay? Is it worth sending people out now, or should the task wait until lighting is better, the thermal conditions are better, or the route is safer? Those are not side questions. In year one, those are the real questions. That is why the first year would feel so hard. The base would not yet have good roads, polished procedures, well-tested route networks, mature storage areas, refined tool systems, or years of local knowledge. It would still be operating in the rough stage, where every EVA is partly productive work, and partly another lesson in how difficult the surface still is. Later crews might inherit something that feels more organised, with better mobility, better maps, better landing zones, and better logistics. The first crew would not get that version. They would be the ones building it, one exhausting EVA at a time. So the romance of moonwalking would not exactly disappear, but it would get pushed into the background very fast. What remains in the foreground is logistics. How far can you go? How long can you stay? What can you carry? What can break? What can wait? And what absolutely has to be finished before you come back inside? The moon would make all of that matter on every trip. It would turn the outside world into a work site, where every minute costs something, and every success depends on planning more than people want to admit. And once every step outside becomes that procedural, the next shift becomes even more serious, because now the crew cannot rely on Earth the way astronauts in low orbit still can. They have to start acting more like local decision makers than visitors taking instructions. The moon would force you to make decisions with less help than any crew before, and that changes the whole feeling of being there. A lot of people hear that the moon is close to Earth, and they assume that means control from Earth would still feel almost immediate. It would not. The distance is still around 384,400 kilometers on average. And even that creates enough communication delay to matter. A one-way delay of about 1.3 seconds does not sound huge until you try to use it during real operations. Then it becomes obvious very fast. Conversation stops feeling natural. You cannot interrupt cleanly. You cannot talk over each other smoothly. You cannot get the same kind of instant back and forth that crews in low Earth orbit got used to. And that matters because a lot of mission culture was built around exactly that fast, tight loop between astronauts and mission control. On the moon, that loop would start breaking apart. Not completely, but enough to change how work feels. If you are trying to get advice during a delicate repair, or confirm what you are seeing during an anomaly, or talk through a problem while you are already under time pressure, even small delay starts getting in the way. It slows rhythm. It creates hesitation. It makes fine real-time coaching less useful. The crew would feel something psychologically strange very early. Earth would still be visible. Home would feel close emotionally. But operationally, Earth would already be a little late. And that delay matters more than people think, because the real problem is not just the seconds. It is what the seconds do to confidence and workflow. In low Earth orbits, mission control can stay tightly coupled to the crew. That means a lot of operations can lean on immediate support. On the moon, that model becomes weaker. If a rover gets stuck, if a suit system starts behaving oddly, if dust contaminates a mechanism, if a thermal issue starts building, mission control can still help, but not in the same way. The support is still there, but it arrives with friction. That friction changes how people act. The crew cannot wait for Earth to drive every response in detail. They have to be ready to interpret the situation themselves, make the first call themselves, and keep moving while support catches up. That is one of the biggest differences between visiting the moon and living there. A visiting crew can tolerate more dependence because the mission is short and tightly scripted. A Year 1 outpost cannot. Too many things can go wrong in a normal week. Power issues, dust intrusion, suit wear, comms dropouts, route problems, thermal drift, medical concerns, equipment faults, timing conflicts. If the crew freezes every time something unexpected happens and waits for Earth to untangle it, the whole base slows down. That is why the first year would be so hard. The crew would have to act more like field commanders and less like remote hands. And once that becomes true, the pressure on every crew member goes up. A young lunar outpost would not have the luxury of paralysis. If life support performance drops, somebody has to decide what gets shut down first. If power margin tightens, somebody has to decide which task slips and which one stays. If dust contamination spreads farther than expected, somebody has to decide how aggressive the cleanup response needs to be. If a crew member starts showing signs of fatigue or stress at the wrong time, somebody has to decide how to protect the mission without damaging the next day's work. Those decisions can involve real trade-offs, and they often cannot wait for a perfect answer from Earth. That means lunar crews would need broader authority, stronger cross-training, and better onboard planning tools than earlier crews relied on. Everyone would need deeper understanding of systems outside their own specialty, because the outpost cannot afford narrow expertise only. A person who mainly handles power still needs to understand enough about life support, EVA timelines, and habitat constraints to make useful decisions under pressure. A person focused on science still needs to understand enough about procedures and emergencies to help stabilize the base if the day goes bad. The moon would push the crew toward local competence in a much stronger way than most past missions did. And that would not just be operationally hard, it would be emotionally heavy. There is a big difference between following procedure in a controlled environment and knowing that your decisions may carry more weight because Earth cannot close the gap fast enough. On the moon, the crew would feel that difference every time something moved off script. People like having backup, and the moon still gives you backup, but not the kind that can stay inside every second of the workflow. That means responsibility starts landing harder on the people actually there. During the first year, that would be one of the hardest adjustments. The crew would be learning in real time how much judgment they have to carry themselves. And the far side shows the extreme version of that problem. Even if the first permanent base is not built there, the far side makes one fact very clear. The moon is not one simple operating area. Some places have delay. Other places lose direct contact entirely without relay support. That matters because it shows how fragile the communications backbone can be if the architecture is still thin. A mission area can look geographically reachable and still be operationally isolated if the right comms infrastructure is not already in place. That raises the importance of relays, local networks, surface repeaters, navigation support, and deliberate communication planning. In Year 1, that whole system would still be young. It would not yet have years of upgrades and redundancy behind it. So communications would not just be a convenience, they would be strategic infrastructure. Which zones have stable contact? Which routes fall into bad geometry? Which operations need relay support? Which assets deserve the best comms coverage? All of that starts affecting what the crew can realistically do. That is another reason the first year would be the hardest. The communication system would still be growing into the job at the exact moment the crew needs it most. And that brings the whole section to the real shift that happens in Year 1. This is the point where lunar crews stop being visitors. That sounds like a small change in identity, but it is actually huge. Visitors can operate like people on a mission. They arrive, follow a tightly designed plan, and leave. A Year 1 lunar crew cannot think like that for long. They have to think like people responsible for a place. That means protecting systems, setting priorities, absorbing uncertainty, making local judgments and carrying more of the mission inside the habitat, instead of assuming Earth will always hold the center of control. That change is not bad in itself. In the long run, it is necessary. A permanent human presence beyond Earth only becomes real when crews can operate with more local authority and confidence. But in the first year, that transition would be stressful because it would still be new, the procedures would still be young, the communication habits would still be adjusting. The tools for onboard planning would still be improving. The crew itself would still be learning how much responsibility really can no longer be pushed back to Earth. So the first year on the moon would feel hard not only because the environment is hostile, but because the culture of human spaceflight would be changing at the same time. The crew would be living through the moment when support from Earth stops feeling immediate enough. And local judgment starts becoming the real centre of operations. Earth would still advise, still monitor, still help, but the people on the moon would increasingly be the ones who have to decide first and explain later. And once the crew has to carry that much responsibility locally, the next problem hits even harder. Because now they are not just working far from home, they are living in sight of it, and still cannot reach it. Isolation on the moon would hit harder than most people expect, because Earth would still be right there in the sky. That is what makes it different from the kind of distance people usually picture in space. If you were going much farther out, the separation would feel absolute. The moon is not like that. In many places, Earth would stay visible, large enough to notice, familiar enough to hurt. You would be able to look up and know that home is still active right now. People are eating dinner there, sleeping there, driving through traffic there, walking outside there, hearing wind there, feeling rain there, arguing there, laughing there, living normal life there. And you are not there. That is the emotional setup of a lunar outpost. Home is not gone. It is visible, but unreachable on any normal human timescale. That would make the first year especially hard, because isolation would not feel abstract. It would feel specific. You would not just miss Earth in a general sense. You would miss details: colour, weather, trees, open space, noise that is not machinery, air that is not processed, movement that is not procedural. On the moon, the absence of those things would stay sharp, because the reminder would stay visible. Earth would not fade into myth. It would keep showing up as a constant reference point for everything you no longer have around you. And that is only the outside part of the problem. Inside the habitat, confinement would make every small human issue much more important than it looks from Earth. A first-year lunar base would not be spacious. It would not be relaxed. It would be compact, highly managed, full of equipment, full of routines, and full of shared dependence. Privacy would be limited. Noise would matter more. Smells would matter more. Delays would matter more. A bad mood would matter more. On Earth, people can cool off by leaving. They can go for a walk, sit alone somewhere, drive somewhere else, get away from the room, get away from the argument, get away from the routine. On the moon, none of that is simple. You cannot just step outside. You cannot casually put distance between yourself and the people you live with. Every separation requires architecture, schedule, and permission from the system around you. That means small tensions would stop being small very quickly. One person being sloppy with procedure is not just annoying, it affects safety. One person being louder than normal is not just irritating. It can hit sleep and concentration in an already stressful environment. One repeated habit, one personality clash, one badly timed argument, one passive-aggressive moment around shared work. All of that carries more weight when the crew is trapped inside a small volume and has to keep functioning as a unit. During the first year, group dynamics would not be a side issue. They would be part of mission stability. And the hard part is that the pressure would not always come as one dramatic event. Most of the time, it would build in smaller, quieter ways. This is where sleep makes the whole problem worse. If your body clock is already off, and your rest is already weaker, then isolation hits harder. Fatigue lowers patience, it lowers focus, it lowers emotional control. Small problems start feeling larger, noise becomes more irritating. Schedule changes become more stressful. A comment that would have been harmless on Earth starts sounding sharper than it should. A minor mistake starts feeling personal. The moon would not need some huge psychological crisis to damage performance. It would just need enough poor sleep, enough confinement, and enough repetition to slowly wear people down. That is one of the most realistic dangers in the first year. Not one sudden breakdown, but a chain of smaller erosions. Slightly worse sleep, slightly worse mood, slightly slower thinking, slightly more tension over procedures, slightly more frustration during maintenance-heavy days, slightly less emotional margin when something goes wrong. That is how an extreme environment often works. It does not always hit you in one obvious blow. Sometimes it keeps taking a little too much, for a little too long, until the whole team feels thinner than it did before. And there is another reason that would be so difficult. Because on Earth, your mood is constantly shaped by things outside of you. On the Moon, almost all of that disappears. On Earth, people reset themselves through the environment all the time without even thinking about it. Going outside changes your state. Daylight changes your state. Seeing a different street, hearing birds, sitting in a park, walking in rain, being alone in a crowd, taking a drive, changing rooms, changing scenery, all of that gives the mind new input. It helps regulate stress. On the Moon, most of your emotional weather would come from inside the base. Crew relationships, work pace, hardware status, mission updates, communication from home. The next maintenance task, the next EVA timeline, the next alarm, the next system check. The habitat itself becomes the main source of variation, and that is not much variation. That means design choices that sound secondary on Earth would become much more important there. Meal timing would matter. Quiet areas would matter. Personal routines would matter. Windows would matter if you have them. Communication rituals with home would matter. Shared downtime would matter. Private downtime would matter even more. A first-year lunar base would need to support mental pacing, not just life support. If the crew has no way to reset psychologically, then stress starts recycling inside the same small environment that created it. And that creates one of the strangest parts of the first year, because the mission itself would start acting like the crew's emotional climate. If equipment is behaving well, the whole base feels lighter. If a system starts failing, the mood tightens. If the schedule gets overloaded, everyone feels it. If communication from home is delayed or emotionally difficult, that enters the habitat too. On Earth, your inner life is mixed with a huge outside world. On the Moon, the outside world is mostly hostile and inaccessible, so the emotional center of gravity shifts inward. The mission, the crew, and the habitat start shaping each other much more directly. A technical problem can become a morale problem very fast. A morale problem can become a performance problem just as fast. That is why the first year would hurt more than later years. A mature settlement would eventually build its own rhythm. It would have routines, traditions, habits, maybe even small comforts, and social patterns that belong to the place itself. People would know what lunar normal feels like. There would be inherited ways of doing things, inherited ways of coping, inherited ways of marking time and keeping morale stable. Year one would have none of that. That is the real emotional difficulty. Nobody would be from the Moon yet. Nobody would have grown up with its routines. Nobody would inherit a stable lunar culture. The first crews would be carrying Earth culture into an environment that does not support it naturally, then trying to reshape it under pressure while they are still learning how to survive there. That means even when the outpost is operational, it still feels psychologically foreign. People are living there, but the place has not yet become normal in the human sense. So the first year would be the hardest. Not just because the crew is isolated, but because they are isolated in sight of home, trapped in a small system, living with weak sleep, limited escape and no local culture, yet strong enough to absorb the pressure. They would not just be surviving an extreme environment, they would be trying to invent a way of being human inside it. And once the emotional strain starts building like that, the next problem becomes even more serious, because even the ground under the base is not as quiet as people think. The Moon is quieter than Earth, but it is not quiet enough to trust. A lot of people still picture the Moon as a dead, stable world, just sitting there with nothing moving, unless humans arrive and start disturbing it. That picture is too simple. The Moon is less active than Earth, but less active does not mean harmless. In your first year, one of the hardest adjustments would be realizing that the ground under your base is not just old, it is still capable of surprising you. That matters because on the Moon, once the ground becomes unreliable, everything built on top of it starts looking less secure. Moonquakes are the clearest example of that. They are real, and some of them are stronger and longer lasting than most people expect. A shallow moonquake can be serious enough to matter to structures, equipment, and surface operations. And the duration changes the whole problem. A short shake is one thing. A long shake is another. If vibration keeps going for minutes, or even longer in some cases, then tanks, masts, solar towers, landing vehicles, connected modules, and exposed hardware all have to absorb that stress. Even if nothing fully fails, the base still pays for it through alignment issues, structural fatigue, inspection time, and reduced confidence in anything lightly anchored. That should change the whole way you think about a lunar base. The moon is not a perfectly still slab of rock, waiting politely for construction. It is stable enough to build on, but active enough that you cannot ignore the risk. In year one, that matters even more because the outpost is still young. The structures are newer, the layouts are less proven, the landing pads may still be temporary, and the crew is still learning what local ground behaviour actually feels like. A mature base may eventually treat moonquakes as a known design condition. A first-year base would still be learning where the margins really are, and the ground is not only affected from below, it is also being hit from above all the time. Earth gets a huge advantage from its atmosphere. A lot of incoming debris burns up before it ever reaches the ground. The moon does not get that protection. That means micrometeorites and other small impactors keep hitting the surface directly. Some are tiny, some are larger, but together they mean the moon is not a still museum piece. It is still being hit, still being chipped, still being altered. That does not mean the whole surface is constantly exploding around you. But it does mean the environment includes ongoing impact risk and ongoing seismic background from those impacts. That changes how you think about exposure. On Earth, small incoming debris is usually not a daily human concern at ground level. On the moon, it becomes part of the environmental reality. Structures need to account for it. Outer surfaces need to account for it. Exposed equipment needs to account for it. Habitat design, shielding, storage, and placement all start looking different when you accept that the surface is still being bombarded. In the first year, that would add another layer of pressure because so much of the base would still be in its more exposed phase. Some systems would still be lightly shielded. Some work areas would still be temporary. Some routes would still be open and unfinished. So the crew would not just be living on old ground. They would be living on ground that is still part of an active impact environment. And that leads to another uncomfortable truth because the same geology that makes the moon scientifically valuable is also what makes it hard to live on. The lunar surface preserves information that Earth has erased. That is one reason scientists care so much about it. Lunar regolith and rock hold records of ancient impacts, volcanic history, solar wind exposure, and parts of early solar system history that do not survive well on Earth because Earth keeps recycling its surface. That makes the moon incredibly valuable as a scientific archive. But the same history that preserved that archive also built the difficult terrain you have to live on. The ground is loose in places, mixed in messy ways, abrasive, cratered, and full of old impact structures. That is not just interesting geology. That is the surface your vehicles drive over, your landing systems disturb, your cables cross, your habitats rest on, and your crews walk across in bulky suits. So the moon's scientific value and its engineering difficulty come from the same source. The bombardment that made it important to study is also what made it awkward to build on. In year one, you would feel that constantly. The place you came to learn from is also the place that keeps making normal operations harder than they should be. Then you get to one of the harshest patterns in the whole lunar story. The best locations often combine several problems at once. The South Polar region is the best example. It is attractive because of lighting conditions that can help power, and because permanently shadowed regions nearby may hold useful water ice. But that same region also includes difficult slopes, extreme cold traps, strange shadow geometry, and faults that may be relevant to shallow moonquake risk. So the area you want most is also an area full of hidden complications. That is the pattern the moon keeps repeating. The useful places are rarely simple places. That matters in year one because early crews would be trying to build knowledge and survival margin at the same time. They would not yet have a complete understanding of which slopes stay reliable under repeated traffic, which shadowed areas distort judgment the most, where dust tends to drift, how much small seismic activity actually matters to operations, or which routes look safe from orbit, but become awkward on the ground. All of that local knowledge has to come from experience. And experience takes time. The first crew would be living in the phase where that map is still incomplete. That is the part people do not usually picture. They think about lunar hazards as a list. Radiation, dust, temperature, low gravity, isolation. But in real operations, those hazards overlap in specific places. A route can be bad not just because it is steep, but because the lighting there is deceptive. A work zone can be risky not just because it is cold, but because it is cold, dark, dusty, and harder to reach if something goes wrong. A building site can be attractive for one reason and dangerous for three others. The moon does not present problems one at a time. It combines them, and that is why the first year would be the hardest. Not because every part of the surface is equally dangerous, but because you do not yet know the surface well enough in practice. You are still learning which dangers matter most in which places. You are still finding the reliable paths, the unstable spots, the bad sightlines, the worst shadow angles, the surfaces that look firm but are less cooperative under load, the areas where repeated traffic causes more trouble than expected, and the locations where operations become more fragile than the map suggested. Later crews might inherit all of that. They might get route networks already tested by real use. They might get marked hazard zones, validated building pads, more detailed seismic understanding, stronger local procedures, and years of lessons that make the environment more legible. The first crew would not have that. They would be producing that knowledge while also depending on it before it is complete. That is what makes year one so exposed. You are learning the landscape while already relying on it. So the moon being quieter than Earth would not make it safe in any easy sense. It would only mean the danger looks different. Instead of weather systems, you get long-term geological roughness and impact damage. Instead of frequent earthquakes, you get quakes that can still matter when your structures are young and your margin is thin. Instead of a living planet that changes fast, you get an old surface that keeps old damage, hides local traps, and still gets hit from space. That is enough to matter a lot when you are trying to build a permanent human presence on top of it. And that is the real first-year problem. The local hazard map would still be unfinished. The crew would not yet have the deep familiarity that turns a hard environment into a manageable one. They would still be generating the knowledge that later people get to treat as normal. On the moon, that learning process is not free. It is paid for in slower work, tighter caution, more inspections, and real operational risk. So the first year would not just be about surviving known hazards. It would also be about discovering which hazards the site has in the first place and how badly do they interact. That is why the moon would stay harder in year one than later on. The place itself would still be partly unknown. An unknown ground is never truly comfortable when your life depends on it. And once even the land under the base can surprise you, the next problem becomes much more immediate. Because now one injury, one illness, or one bad accident can turn the whole outpost into an emergency system at once. And once the ground, the dust, the radiation, and the isolation are already working against you, the next problem becomes the one that can stop everything at once, a medical emergency. This is where the moon stops feeling distant in a romantic way and starts feeling distant in a very practical way. Earth is not infinitely far away, but it is not close in the way that matters during an emergency. There is no lunar emergency room around the corner. There is no ambulance. There is no hospital staff waiting 10 minutes away. There is no fast evacuation that you can trust the way people trust emergency systems on Earth. Distance, communication delay, launch readiness, vehicle status, surface conditions, airlock turnaround, and the sheer complexity of leaving the moon all combine into one hard truth. If somebody gets seriously hurt, the crew on site becomes the medical system. That changes the meaning of injury immediately. A bad fall is no longer just a broken bone problem. An eye contamination event is no longer just an eye problem. A decompression issue is no longer just a pressure problem. A breathing issue, a burn, a cut, a suit puncture, a severe fatigue event, any of these can force the whole outpost into emergency mode. And in year one, that would feel even worse. Because the base would still be young. The systems would still be early. The procedures would still be tested in real conditions for the first time. So when something goes wrong medically, you are not handling it inside a mature colony with deep support. You are handling it inside a fragile outpost that is still trying to prove it can function at all. And what makes lunar medicine especially hard is that the risks are all connected. On Earth, people often separate health problems into categories. Injury is one category, sleep is another, air quality is another, stress is another. On the moon, those categories start feeding into each other. Low gravity may weaken muscles and bones over time, which raises injury risk. Poor sleep can slow judgment and reaction time, which raises accident risk. dust can irritate eyes and airways, which makes EVA recovery and habitat hygiene more complicated. Radiation adds long-term exposure concerns and sometimes short-term operational constraints. Stress and confinement can lower focus, increase conflict, and make people more error-prone. So health on the moon would never be just about treating isolated problems. It would be about constantly managing a whole chain of environmental pressures before they combine into something worse. That means a first-year lunar medical system could not just be a cabinet full of bandages. It would need constant monitoring. Are people sleeping well enough? Are exercise routines actually protecting muscle and bone? Is dust exposure staying within control? Is fatigue creeping up? Is somebody starting to compensate for pain or weakness in a way that raises injury risk later? Is the crew's stress level starting to affect performance? Those questions would matter because the moon turns health into a systems issue. If the body starts degrading slowly, operations get more dangerous before anybody is officially sick. And that gets even more serious the moment something happens outside. An EVA injury on Earth would already be serious. On the moon, it becomes a full mission cascade. If one astronaut is hurt during an EVA, that does not stay one person's problem. Now, another crew member may need to assist or drag equipment or help stabilize the injured person. The route home matters immediately. Suit consumables matter immediately. Airlock prep matters immediately. The habitat may need to shift roles instantly from normal operations to medical intake. Somebody has to track oxygen, battery, thermal condition, and timeline while also thinking about treatment. Somebody may need to talk to Earth, but not wait too long for Earth. Somebody has to start protecting the rest of the mission while the emergency is still unfolding. That is why medical problems on the moon are not just dangerous. They are expensive in crew bandwidth. A small crew has limited redundancy. If one person goes down, another person may be pulled off duty to help. A third may have to take over an essential task. A fourth may be stuck reworking the whole schedule, the EVA plan, the habitat workload, and the resource margins. So even a non-fatal injury can damage the base in multiple ways at once. You lose capability, you lose time, you lose flexibility, and you increase stress across the whole group. In year one, when teams are small and margins are thin, that kind of disruption would hit hard. And because evacuation is difficult, the habitat itself would have to behave more like a clinic than people usually imagine. That does not mean a full hospital. It means the base would need to be designed around prevention, diagnosis, and local care much more seriously than a normal mission habitat. You would want onboard diagnostics, enough sterile capability for basic procedures, strong contamination control, exercise systems that are treated as medical equipment, not just fitness equipment, and routines for sleep, mental health, and body monitoring that are built into daily life. The medical system would not sit off to the side waiting for disaster. It would be woven into the structure of the outpost from the beginning. That is because on the moon, prevention matters more when rescue is weak. If a problem can be caught early, that matters. If fatigue can be reduced before it causes an accident, that matters. If a dust control rule prevents airway irritation or eye contamination, that matters. If a crew member's physical decline is noticed before it causes a bad fall during EVA, that matters. In year one, medicine would not mainly be about dramatic intervention. It would be about keeping the crew inside a narrow band where everything is still manageable. And this is exactly why the first year would be harder than later years. A mature settlement may eventually have larger crews, more medical equipment, better local manufacturing, thicker supply reserves, stronger isolation space, more specialised training, and more realistic evacuation options. Year one would have almost none of that. It would have fewer people, fewer backups, fewer spare systems, fewer comfortable margins, and a lot more dependence on procedures working correctly the first time. So every medical problem would be magnified by the youth of the base itself. A minor problem in a mature settlement might stay minor. The same problem in year one could become a major operational event because the whole outpost is still thin, still small, still learning, and still easy to disrupt. That is the real pressure. You are trying to keep human bodies healthy inside an ecosystem that is barely stable enough to host them. So the first year on the moon would not just test whether you can treat injury and illness. It would test whether the base can absorb them at all. One bad incident could consume crew time, power, oxygen, schedule margin, emotional stability, and confidence all at once. And when a place is still that young, every emergency reveals the same thing. Survival is not only about the outside environment, it is also about how much weakness still exists inside the base itself. And that is what leads to the final point. Because by the end of year one, the hardest truth would be clear. You were never just living on the moon. You were inventing how. The hardest part of the first year would be this. You still would not really be living on the moon. You would be inventing how to live there. That is the difference that explains everything. People often assume the hardest part is launch, landing, or the first step onto the surface. Those things are hard, but they are short. Year one is different. Year one is when the mission stops being a visit and starts trying to become a presence. That is a much bigger challenge. It means every system that looked good in planning now has to survive real dust, real cold, real delays, real fatigue, real terrain, and real human error. A base on paper can look clean and logical. A base on the moon has to deal with the moon as it actually is. That is why the first year would feel so difficult from the first month onward. Every life support loop, every airlock rule, every suit procedure, every power layout, every sleep routine, every EVA timeline, every cleaning method, every shielding decision, all of it would still be proving itself under real conditions. The design phase would be over, but the real test would only just be starting. And the moon would get a vote on every part of it. The ground would get a vote, the dust would get a vote, the lighting would get a vote, the weak gravity would get a vote, the cold traps would get a vote, the radiation would get a vote. That is what year one really means. It is the moment the blueprint hits the surface and the surface starts pushing back. And the first crew would pay the full price of that immaturity. Later crews would inherit things that the first crew had to build the hard way. Better landing pads, better route maps, better lighting knowledge, better dust control procedures, better power placement, better thermal rules, better shielding, better emergency drills, better maintenance schedules, better understanding of what breaks first and what lasts longer than expected. Later crews would also inherit something even more important than hardware: local knowledge. They would know which slope is worse than it looks, which storage area collects more dust, which cable route turns into a problem in low-angle light, which EVA tasks always take longer than the schedule claims, which systems need more protection than early planners thought. The first crew gets almost none of that. They get early versions. They get prototypes, partly tested procedures, incomplete confidence, and systems that may have worked in simulations and field tests on Earth, but have still not been proven where they now matter most. That is why the moon hits year one harder than later years. Not only because the environment is harsh, but because the human answer to that harshness is still unfinished. The response system is still being built, while people are already depending on it. That is the deepest challenge of the whole story: operational thickness. A place starts becoming livable when it gains layers: backup power, backup water, spare parts, buried habitats, protected landing zones, clean work areas, marked routes, safer storage, practiced routines, reliable repairs, and confidence that one bad day will stay a bad day, instead of becoming a disaster. That is what makes a harsh environment more manageable over time. It gets thicker. More options, more redundancy, more local skill, more margin. Year one on the moon would have almost none of that thickness. The shielding would still be thin. The infrastructure would still be thin. The spare margin would still be thin. The crew count would still be thin. The local industry would still be thin. The medical system would still be thin. The psychological cushion would still be thin. The tolerance for error would still be thin. And that one idea explains almost everything in this entire video. The first year would be the hardest because lunar civilization would begin thin. That is why every problem feels bigger in year one. A dusty airlock is not just annoying because the cleaning system is still limited. A power shortfall is not just an inconvenience because the energy margin is still small. A medical issue is not just a health issue because the whole base is still easy to disrupt. A bad route is not just a bad route, because there may not yet be many proven alternatives. A communication delay is not just a delay, because the crew is still learning how much authority it must carry locally. Everything feels sharper when there are fewer layers between the problem and the people living inside it. But this is also where the story turns, because after that first year, the moon starts changing shape in human terms. Not physically, of course. The moon does not become friendly. It does not become easy. It does not become Earth-like. But it does start becoming legible. Regolith stops being only dust and starts becoming shielding. Ice stops being only a target on a map and starts becoming water. Oxides stop being just chemistry and start becoming oxygen. Routes stop being guesses and start becoming roads in the practical sense. Power stops being a constant emergency calculation and starts becoming something more stable. Procedures stop feeling experimental and start feeling normal. Crew culture stops being imported under pressure and starts becoming local. That is the hinge point. Before it, the moon is mostly visited. After it, the moon can start to be inhabited. That does not mean the danger goes away. It means the danger gets understood better, managed better, and absorbed by stronger systems. A mature outpost would still respect dust, radiation, weak gravity, harsh temperature shifts and isolation. But it would no longer be surprised by them in the same way. It would have habits built around them. It would have design choices built around them. It would have routines that turn some of the daily strain into something more sustainable. That is what the first year is buying at such a high cost. Not comfort, not safety in the full sense, but the beginning of familiarity. And that is what really changes how you should think about the moon. For a long time, the popular image was simple. The hardest part is getting there. Build the rocket, make the trip, land successfully, and the main battle is over. But that idea falls apart once you look at what long-term lunar life actually demands. Getting there is only the entrance exam. The real test begins after touchdown, because once you are there, gravity changes the way you move. Time stops matching your biology. Temperature starts attacking every exposed system. Radiation controls your schedule. Dust follows you everywhere and slowly eats machines. Your suit becomes a personal spacecraft that never lets you relax. Water sits in hostile places. Oxygen is trapped inside rock. Food production is possible, but hard. Power becomes survival. Shelter takes far longer to become real than people assume. Every EVA becomes a logistics problem. Autonomy becomes mandatory. Isolation becomes sharper because Earth is visible. The ground itself is quieter than Earth, but still not quiet enough to ignore, and one medical emergency can consume the entire base. Put all of that together, and the answer becomes very clear. The first year on the moon would be the hardest because the moon does not care that you arrived. Arrival is not success there. Arrival is permission to start solving the real problems. That is the part that changes everything. The moon does not reward courage by itself. It does not reward symbolism. It does not reward planting a flag and calling the job done. It rewards adaptation, and adaptation takes time. It takes mistakes, redesigns, maintenance, discipline, local knowledge, and systems that get stronger month by month. In year one, almost all of that still has to be created under pressure. That is why year one is so brutal. It is the year when every weakness is still exposed and every solution is still incomplete. So the first year on the moon would be the hardest, not because humans are incapable of living there, but because the first year is the price of finding out how. It is the year when every routine is still being invented, every safeguard is still being tested, every margin is still too thin, and every success still costs more effort than it will later. You are not stepping into a finished world. You are building the first rough version of one. And that is the final point. The moon would not become a place for humans the day people land there and stay. It would become a place for humans only after one long, difficult, expensive year of learning how not to lose against it. That first year is where a mission turns into a foothold, and where a foothold starts trying to become a civilization. That is why your first year on the moon would be the hardest. Not because the moon would beat you all at once, but because for one full year, every day would be teaching the same lesson. You are not there to enjoy a new world yet. You are there to make that world barely livable, One fix, one procedure, one hard-earned adaptation at a time. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video